Hello everyone, today I will present our work called RegGS, Unposed Sparse Views Gaussian Splatting with 3DGS Registration. This work was done in the 3D Agent World Lab at HKUSTGZ, and it has been accepted to ICCV2025. The problem we study comes from 3D scene reconstruction and novel view synthesis. Traditional NERF works very well for novel view synthesis, but it strongly depends on known camera poses, and the training cost is very high. Later, 3D Gaussian splatting was introduced. It makes rendering and reconstruction much more efficient, but when the views are sparse, optimization-based methods lack geometric priors, so they often suffer from topology breaks and scale ambiguity. Another line of work is feed-forward 3DGS models. These models use large-scale data priors to directly predict local 3D Gaussian. They are robust when camera poses are missing or when only a few views are available. But they can only handle a small number of inputs and cannot scale to large or complex scenes. So the key challenge is, how can we fuse these local Gaussians, predicted without camera poses, into a globally consistent 3D representation? Our framework is called RegGS. The pipeline is simple. We use a feed-forward network to extract local Gaussians from the input images. Then, these local Gaussians are progressively registered into a global representation. This allows us to achieve high-quality 3D reconstruction and novel view synthesis. The core problem here is how to measure the similarity between two sets of Gaussians. To solve this, we introduce a new metric, the mixed second-order Wasserstein distance, or MW2. With Sinkhorn approximation, it can be solved efficiently, and it captures the spatial closeness of two Gaussian sets. More specifically, each local submap is a set of Gaussians. Our goal is to find a Sim3 transformation that aligns each local set to the global space. The MW2 distance builds on the closed-form formula of Wasserstein 2 distance between two single Gaussians and extends it to mixtures of Gaussians. By adding entropy regularization and using Sinkhorn approximation, the distance becomes stable and differentiable. This makes Gaussian set registration end-to-end trainable. However, MW2 alone can only provide coarse alignment. To improve accuracy, we add two more constraints: photometric consistency and depth consistency. MW2 ensures global alignment and avoids large errors. Photometric consistency refines the alignment at the pixel level. Depth consistency reduces scale drift by using depth maps. The final loss is a weighted sum of these three parts. With this joint optimization, RegGS can generate local Gaussians and align them step by step in Sim3 space, finally fusing them into a globally consistent representation. In experiments, we first evaluate on the Re10K dataset. Our method clearly outperforms other unposed methods under sparse views, and the gap becomes larger when the number of input views decreases. This shows that RegGS is especially strong when the data is very limited. We also test on the ACID dataset. The results show the same trend. As the scenes become sparser, our method performs even better compared with the baseline. This means RegGS is robust both in indoor and in large-scale outdoor scenes. We also evaluate pose estimation accuracy on both Re10K and ACID. Under different numbers of input views, our method again outperforms the baselines. This result is important, because even though we never use external camera poses, our method still learns more accurate relative geometry during the registration process. This directly benefits both reconstruction and rendering. To conclude, I want to highlight three main contributions. First, we propose a MW2-based Gaussian set alignment in Sim3 space. Second, we design a differentiable joint optimization module that combines MW2, photometric, and depth consistency, which effectively reduces scale drift and improves alignment. Third, we achieve significant improvements over existing unposed methods on multiple datasets, and our advantage is especially clear when the number of views is small. This is our work. Thank you very much for listening.